Hello again. So let's look at our problem. If A, B, and C are positive numbers such that A plus B is greater than C, A plus C is greater than B, and B plus C is greater than A, then show that there exists a triangle with side lengths A, B, and C. So this is basically the converse of the triangle inequality theorem. It's saying if these lengths fit this situation and show we can absolutely make a triangle out of that. So let's just assume that A is greater than or equal to B, which is greater than or equal to C. It doesn't matter in which way you arrange them. You could put B is greater than all of them or whatever. But there has to be some order to it, or they're all equal to each other. So I'm just going to assume A is the greatest or equal to B, which is greater than or equal to C, which would be the smallest or equal to the rest. And therefore we're going to have some triangle where like AB is going to have the length of lowercase c, and AC is going to have the lowercase b length, and then BC is going to have the lowercase a length. So let's kind of examine what this situation is going to look like. We know A is the largest length, so let's kind of start off the problem with this length here, BC, which we called A, lowercase a. Then we know that we can make a, whatever point that uppercase A would be on has to be located on the circle that has a center at B and a radius of, what do we say B? BA is lowercase c, so that would be the smaller one. So somewhere around here. And so, you know, somewhere on this circle, it doesn't even necessarily have to be that point, but somewhere on this circle is uppercase A, or where we would like that to be. But we're going to call the radius of the circle, let's call this point, I don't know, point D, where it fits on the line itself, where it fits on the line BC. So that means that when we go back, this distance here is going to be the distance lowercase c. Now we can do the same thing with a circle at center C. But since the distance we want is now going to be that lowercase b distance, it's strictly greater than C. So it's the distance of C, but more than that, so it has to kind of surpass that length. So this point over here, which we are going to change the label to, let's change it to E. So now we have that CE by construction is equal to the distance lowercase b. We have that BD is the distance of lowercase c, and BC has the distance of lowercase a. Now, because that we have lowercase a is greater than or equal to lowercase b, which is greater than or equal to lowercase c, then we know that that distance of b, that lowercase b, which is CE, surpasses the distance of C. So that means the two circles are basically meeting at two different points that we see here and here. because the larger circle that has a radius of B must surpass the circle that has a radius of C. And because of that, we have these two intersection points, and therefore I'm going to call this uppercase A. And I can note that, well, since this intersection is the radii of the circle at center C, then I know that since all radii have the same length, that this distance must be that lowercase b that I was talking about. And the same logic can give us that the distance from B to that point, A, also has that distance that we know that is C. Because again, it's the radii of the circle at center B. So like BA has the same distance as BD. So let's just say BA is equal to C as well. And we also know that CA is equal to B as well. And therefore, we have constructed a triangle. Well, we have two possible triangles, but we made one where we have determined that each side of the triangle satisfies that condition we started with, this one, and is an actual triangle since it's three-sided, has the lengths A, B, and C. So what we've determined is that given those starting conditions, we now know we can indeed construct a triangle out of this problem.